Hi guys, it's Mrs. Millison. Okay, we're going to talk about gathering data, and this is section 4.2 in the books, specifically about experiments. Okay, but first let's talk about all the ways we're going to gather data. Okay, first one is an observational study. This is where we just sit back and observe something that's happening. Okay, so something like if I want to find out the true proportion of cars in Jefferson County that are red, I can randomly pick a intersection and go stand at that intersection one day and count all the red cars out of the total cars. That would be an observational study. I'm not making anything happen. I'm just standing back and watching. Okay. Some observational studies are done over time, and those are called prospective. Things like that are usually when you want to kind of see how something impacts somebody over time, like nutrition or some educational experiment. So you look at the information, you look at the subjects over time to see how they're being impacted. Retrospective is when you use data from the past or data that's already been collected. I think the biggest example of that would be from the census. So every 10 years when we get our census, a lot of researchers use that data throughout the 10 years. Okay. Second way of gathering data is a survey, and we've talked a lot about surveys. Surveys are simply where you ask people questions. Okay. So again, you're not making the subjects do anything, you're just asking a question. Okay. And then the third way of gathering data is in an experiment. Now, in an experiment, we are actually going to impose a treatment. We're going to ask our subjects to do something specific. Okay. Now, with the first two, observational studies and surveys, we can see if there's correlation between certain variables, but we can't say causation. Okay. Remember, correlation just says there's a relationship, it doesn't say one thing causes the other. An experiment is the only time that we can say something causes something else, okay? Because we are actually making the individuals, the subject, do something. So when we get a result, we can say that what we made them do caused that result. Okay, so let's talk about experiments. All right, you need 4 parts of an experiment. Randomness is the first part. Okay, we want to make sure we take a random sample, and we also want to randomly assign treatments. Okay. A control, we need a control. We need a baseline for comparison. So when we compare our results, we can see whether it was different than what we would expect. Okay. A lot of times our baseline for comparison is one of the treatments is no treatment or a dummy treatment or a placebo, and we'll talk about that. Or another way of control is to make sure your treatment groups are as similar as possible. And we'll explore the whole makeup of an experiment so you understand treatments groups coming up. The third part is comparison. And this is a type of control. So at the end of your experiment, you're going to compare the different treatment groups and what the response variable was from them. Okay. And the last one is replication. Replication simply means 2 things: that you have a large enough sample size, and that if somebody else was to repeat your experiment, they would get similar results. Okay. Um, so you need those four components of experiments. And the reason we have to have all 4 of those components is to minimize the effects of confounding variables. Now, confounding variables are uncontrolled variables that can interfere with your results. Okay, so we use randomness, we use replication, we use control to try to minimize the effects of those confounding variables, those variables that we can't control. Okay, so let's talk about parts of an experiment. We have explanatory variables, and those end up being the treatments that we're going to impose. Now, treatments have factors and levels. The factors are the actual variable that will be manipulated, and the levels are the different manipulations. Okay, and you'll see when we do an example. Then we have a response variable. So the response variable is what we measure after we impose the treatment. All right. So let's look at an experiment. We're going to test some migraine medicine. We want to test a new migraine medicine. Okay. Now, unfortunately, we can't randomly select our sample because we need volunteers of people who suffer from migraines. And in a lot of pharmaceutical experiments, you don't have random sampling because you have to have volunteers that have the medical condition that the medicine will work with. Okay. So we'll talk about at the end of this, we'll talk about what's the impact of that. Okay. So our explanatory variables are going to be basically there's only one factor here, and it's going to be the pill that the person's going to take. So this factor, the pill, is going to have 2 levels. The subject's either going to take a migraine medicine or a placebo. Okay. Now we're going to sorry, and they become the 2 treatments. Okay, so the migraine medicine and the placebo are the 2 treatments. Now those 2 treatments will be randomly assigned, to half, so the half of the treatment group, half of the subjects will get the migraine medicine and half of the subjects will get the placebo, and we will do that randomly, okay? I don't know, pull their names out of a hat. First half of the people get the placebo, the second half of the people get the migraine, or some other random way, okay? Then we give them migraine medicine or the placebo for a couple months, and then we ask them to come in and we gather the information for the response variable. This is what we're going to measure. So we ask them how many numbers of headaches they had over the last couple months, how long the headaches lasted, and the severity of the headaches. And then what happens at the end, if our results show that the medicine works significantly better than the placebo, we can conclude that the migraine medicine actually caused migraine pain relief. Okay. Um, that's our cause and effect. And we can say that because we randomly assign the treatments. Now, we can only say that the medicine was effective for this group of subjects. We can't say it's effective for all migraine sufferers because we did not randomly sample our individuals at the beginning. Okay, so there's a little bit of tweaks we have to do here. Okay, let's talk a little bit about ways to make this experiment better. Okay, we'll talk about blinding. Single blind is when the subjects who are receiving the treatments don't know if they're getting the real medicine or the placebo. Okay. Double blind would be the subjects receiving the treatment don't know what they're getting, and the researchers administering the treatment or who are interacting with the subjects also don't know. Somebody knows. Somebody had to prepare the placebos and the medicine to give to the subjects, but the 2 people interacting don't know. Okay. And what this does, this helps to minimize any kind of unconscious bias that can be communicated through body language or something like this that's hard to control. So, if, say, we didn't double blind this experiment, and if I'm the researcher and I'm handing you the migraine medicine or the placebo, I might have some body language or some inflection in my voice that might lead you to think, oh, I think that she's giving me the placebo. Okay. So if the experiment's double blind, there can't be any of that um, subconscious or unconscious, body language indicators that you're getting the real treatment or the placebo. Okay. Um, Double blinding is always better. All right, so some things that can still happen even though we blind are called the placebo effect. The placebo effect is when a subject responds favorably to the placebo or to the dummy treatment, and that can mess with our results. Okay, so if we think the migraine medicine is better, but some of the subjects that took the placebo also say that they had fewer migraines, that can mess with our results. Okay, so it's another good reason to blind, at least single blind, but definitely double blind if you can. Okay. All right, so let's talk about a completely randomized design. Okay. We're going to do something a little bit more than just the migraine medicine. Now we're going to do an experiment to see if migraine medicine and exercise relieves headaches. Okay. So let's talk about our treatments. We have 2 factors. We have the medicine and exercise. The medicine factor has 2 levels. They're either going to get the real medicine or they're going to get a placebo. And the exercise has 3 levels. A subject's either going to do cardio exercise, flexibility exercise, or no exercise. So we combine these into the 6 total treatments. So I'm going to have 6 treatment groups. Some people are going to take the real medicine and do cardio exercise. Some other people are going to take the real medicine and do flexibility exercises, and so forth. Okay. So half my subjects will be getting the real medicine, half will be getting the placebo. Okay. A third will be doing cardio, a third will be doing flexibility, and a third will be doing no exercise. And of course, that last treatment group of the placebo and no exercise, they're my control because they're not taking any medicine, they're not doing any exercise. Okay. And then we say we randomly assign 10 subjects to each of the treatment groups. So I guess we have a total of 60 subjects for our sample. Okay. So we send them off, we tell them to take the medicine or take the placebo or take whatever they're given, do the exercise for a couple months and see what happens. So when they come back, again, we have the response variable. We're going to ask them how many headaches they had, how long were their headaches, and the severity of the headaches. And then we're going to compare all those measurements among the treatment groups to the control. Okay. So if it comes back that the group that took the real medicine and did cardio, or took the real medicine and did flexibility exercise, had a significant decrease in the number of headaches, the length of the headaches, and the severity of the headaches, we could say that the medicine and exercise helps decrease migraine pain. Okay. Um, because we did our random assignment of treatments. Okay. Again, if this group was volunteers, we couldn't say that that's true for all migraine sufferers. We would just have to say it's for our group of subjects. But that's typical in pharmaceutical experiments. Okay. Could we have blinded this experiment? We could have definitely blinded for the medicine. So we can make the medicine and the placebo look exactly the same, and the people in all the treatment groups, they wouldn't know what they're getting. Now, we can't blind for the exercise part. If you're going to do cardio, you know you're doing cardio. If you're not doing any exercise, you know you're not doing any exercise. So sometimes you can blind, sometimes you can't. Okay, let's look at this experiment from graphing standpoint. Whoops, I hit my thing too fast. Okay, we have our 60 volunteer migraine sufferers. We're going to randomly assign 10 subjects to each of the treatments. Okay, so each of the treatments has 10 subjects. And then we will let them take the medicine for a couple months, and then we'll come back and we'll compare the number, duration, and severity of their headaches. Okay, so sometimes people will write out an experimental design. Let me go backwards. Looking like this, where you just kind of write through what you're doing. And some people like to write it as a flow chart. Okay, it doesn't matter which way you want to do it. It all says the same thing. Okay, all right. Let's take this experiment one step further. Let's say there was a previous study that showed that women respond more favorably to the medicine. So what we want to do is we want to take our 60 volunteer migraine sufferers and we want to block by gender. Now, blocking is just like stratifying. You break up for stratifying, you break up your population into groups and then grab a few from each group. But in blocking, you take your sample that you already have. Okay, we had our 60 volunteers, and you break them up into groups. Okay, so we're going to take our 60 volunteers, we're going to break them up into groups by gender. Okay, so we're going to have 25 men and 35 women. Now, the important thing to know about blocking is you have to have a reason to block. The reason we're blocking is because previous studies show that women respond more favorably to the medicine. So the reason we block is so that we can make sure that men and women will each get each of the treatments. Okay. If we didn't block and we just randomly assigned 10 people to each group, I could conceivably have gotten the 25 women all in the medicine treatments. Okay. And none of them would have taken the placebo, or vice versa. The 35, did I say 25 women? I can't remember. The 35 women could have all been put in the placebo group. Okay. So to avoid all of one gender being given like all of medicine group or all the placebo group, we block. So then what we're going to do is we're going to take a few men and a few women and put them into each treatment group. So we're going to randomly assign, say, 4 to 5 men to each treatment group and 5 to 6 women to each treatment group. So now I know that some men and some women are going to get the medicine and the placebo. So that previous study that showed that women respond more favorably to medicine, I've kind of evened it out a little bit on my treatments, or on my assignment of my treatments, by blocking the men and the women. Okay, because again, if all the men had gotten the medicine group, then maybe the medicine doesn't work that well on men, and then my experiment shows that the medicine doesn't work that great, but it really works well in women. But in my just randomly assigning them, the women were all in the placebo. So blocking will ensure that every subgroup of the sample will get every different, or at least will get all the treatments. I can't even figure out what I'm saying. Okay. So again, at the end, we ask them about their number, duration, severity of their headaches, and we compare everything. Okay. So remember, the most important thing about blocking is you must have a reason to block. Okay, I've emphasized that a little bit. So you're told previous studies or something like that, you have to have a reason to block. You can't just block because you want to. Okay, that's very important. Okay. One kind of block design is called matched pair. What matched pair does, it has us pairing up the subjects, okay, and then giving each one of the pairs one of the treatments, okay. So for like our migraine medicine example, I could maybe pair the subjects by gender, age, weight, things like that, so that like I could have two women about the same age, the same weight. Then I would randomly give one of them the migraine medicine and one of them the placebo. Okay. So again, you're trying to minimize any kind of other outstanding variable, any other uncontrolled variable, and a confounding variable. Okay. Um, the best matched pair is when each subject gets all the treatments in random order, of course. Okay. And the best example of this I can think of was when I was younger, there was a TV commercial about a mosquito repellent. So I'm just going to show you that commercial real quick.
Now you can end the irritating misery of mosquito bites with Off, the mosquito repellent that really works. Here's proof. This research man is putting his arm into a cage of hungry mosquitoes. Look at those mosquitoes go for that unprotected arm. Now he sprays the same arm with Off. And just look, they don't bite, they don't even light, because Off contains the world's most effective repellent ingredient. Get OFF, Off, the mosquito repellent that really works.
Okay, so in that example, I didn't have to pair the subject. The subject, the man, had all the treatments. He had the placebo, which was no mosquito repellent when he put his arm in the cage first, and then he actually got the treatment. He got the mosquito repellent and then put his arm in the box. So that is the most ideal matched pair, where every subject gets all the treatments. Sometimes that's difficult to do. Okay. Oh, sorry, there's my little mosquito guy. Okay, so again, in our migraine medicine experiment, I could have had each subject take the migraine medicine for a couple of months and then take the placebo for a couple of months, or reverse order. I would do the random order, okay, and then analyze those results. But sometimes it's hard for one subject to take all the treatment. So that's why we can still try to pair our subjects up and make sure we give them, and make sure of the pair, one gets one treatment, the other gets the other. Now, for that experiment where we had 6 treatments, I would try to find 6 of my subjects that were similar. That's kind of harder to do. Okay. So the more treatments you have, matched pair is a little harder to do. Okay. So the ideal experiment has random sampling, okay, and we can block the sample if we have a reason to. And again, blocking is just like stratifying, but we break our sample up into groups after we have our sample, okay, and we have to have a reason. The ideal experiment has random assignment of treatments, and why? Well, it has to have a control, okay? So we're going to have a placebo, or to make the treatment groups as similar as possible, okay? So that again, all of these things are helping minimize any kind of confounding variables, okay? If we can blind, we should blind. If we can double blind, we should double blind. If I can do a match pair, if I can have every subject have take every treatment or do every treatment, of course, not at the same time, in random order, then that would be ideal also. Okay. And again, the reason we want random sampling and random assignment of treatments is to impact or to minimize the impact of any kind of confounding variable, any kind of uncontrolled variable. Okay. So the reason, or the most important part, is randomness. Okay. Randomness. So if we can random sample, then we can take our results and infer them back to a larger population. Okay. If we do random assignment of treatments, then we can say cause and effect. Okay. So the most ideal, here I emphasize random, the most ideal experiment has random sampling, random assignment of treatments, and all that other stuff. And the important reason being is that I want to be able to take my results and say, it'll apply to the entire larger population. And I want to take my results and definitively say that this causes that. Okay. So those are the elements of an ideal experiment. Okay, I hope this was helpful, and I will see you later.